Hey everyone, welcome to the Explainer. Today, we're going to crack the code on a huge concept in linear algebra, vector independence. Now I know, it sounds a little intimidating, but trust me, it's the secret sauce behind everything from how your photos get compressed to how 3D video games work. So let's jump in and figure out what it really means, and more importantly, how you can spot it in a flash.
So, let's start with a simple idea. Imagine you're an artist and you've got a few cans of paint. How do you know if that brand new color you just bought is actually unique? Or could you have just mixed it yourself from the colors you already had? That's exactly what we're asking with vectors. Are they each bringing something new to the party? Or is one of them just a freeloader, a redundant mix of the others? To figure this out, we use a fantastic tool called a linear combination. The best way to think about it is like a recipe. We take a pinch of vector 1, a dash of vector 2, and so on, and we see if there's any possible combination, any recipe, that makes them all perfectly cancel each other out and land us at 0. It sounds simple, but this one little test tells us everything we need to know.
All right, so how do we know if our vector ingredients are truly special? Well, mathematicians have this one super elegant test, and it all comes back to that recipe we just talked about. I like to call it the all zeros rule, and you're going to see it's way simpler than it sounds.
This right here, this is the golden rule. Pay attention to this. If the only possible way to make your vector recipe add up to 0 is to use 0 of every single ingredient, well then you know they're independent. It's like they're all pulling in such completely different directions that there's just no way for them to cancel each other out unless you don't use them at all.
So really, it all boils down to two possible outcomes. On the left, you've got the ideal situation, linearly independent. This means to get to 0, every single one of your scalars has to be 0. Your vectors are truly unique. But on the right, if you can find a recipe where you use non-zero amounts of your vectors and still get to 0, that's what we call linearly dependent. And that's a huge clue that there's some kind of hidden relationship there, some redundancy.
Okay, so the theory is cool, but you're probably asking, how do I test this without spending all day on it, right? Let's open up the mathematician's toolbox. First up is a tool called the determinant. It's a fantastic, straightforward test, but it's got one catch. It only works if you've got a square set of vectors. You know, like 2 vectors in 2D space or 3 vectors in 3D space. And the process is a piece of cake. Seriously, it's just 3 steps. First, you just line up your vectors as the columns in a matrix. Step 2, you crunch the numbers and find the determinant. And finally, step 3, you just look at the answer. Is it 0 or is it something else? That's it.
And here's the best part. The rulebook couldn't be simpler. If that determinant you calculated is anything, literally anything, other than 0, congratulations, your vectors are linearly independent. But if it's exactly 0, bam, they're dependent. It's a clean yes or no answer. But what if your matrix isn't square?
So what do you do when you don't have a nice, neat square matrix? For that, we need a more powerful, more flexible tool. And that tool is the rank. Just think of rank as the true number of unique directions your vectors are pointing in. It's an awesome shortcut that works for any matrix, no matter the size.
Now, let's walk through the steps, and you'll see it's pretty familiar. Step 1 is the same. Pop your vectors into a matrix as columns. Step 2, instead of finding the determinant, you calculate the matrix's rank. And now, for the final most important step. You simply compare that rank to how many vectors you had in the first place.
Let's make that real for a second. Let's say you start with 3 vectors. You put them in a matrix, you find the rank, and the answer is 2. Well, since 2 is less than the 3 vectors you started with, you know immediately they are dependent. It really is that straightforward.
So here's the rulebook for the rank test, nice and simple. If the rank is equal to the number of vectors you have, they're linearly independent. If the rank is less than the number of vectors, they're linearly dependent. That's it! And because this works for any shape of matrix, it is an incredibly handy tool to have.
Okay, so we've got these 2 powerful tests, the determinant and the rank. But let's get to the big question. So what? Why do we even care if a bunch of vectors are dependent or independent? Well, this is the part where all that theory smacks right into the real world.
All right, if you remember one thing from this whole explainer, let it be this. Linear dependency is just a fancy mathematical term for redundancy. That's all it is. When a set of vectors is linearly dependent, it means at least one of them is completely unnecessary. It's not bringing any new, unique information to the system.
Let's really unpack that. A dependent vector is basically just a copycat. You can create it perfectly by just mixing and matching the other vectors you already have. It's not carving out its own path in space, it's just following a path that the others have already laid out. So when you find dependency, what you've really found is a hidden connection that shows your set of vectors isn't as efficient as it could be. And this quote from the source material absolutely nails it. Finding linear dependency is the exact same thing as finding a secret formula that links your vectors together. You've just proven that they aren't totally separate after all. They're connected.
So if we know that dependency means we have redundant, unnecessary vectors, it leads to a really interesting question, doesn't it? What's the absolute minimum number of vectors we actually need to describe a system? And that question right there is the doorway to some of the most powerful ideas in math, like basis and dimension, the literal building blocks of modern science and technology. But that's a story for another explainer. Thanks for tuning in.